So before we dive into what was discovered about the ocean's floor, let's take a look again at what Wagner's theory stated with continental drift. So remember, Wagner basically said that the continental crust moved, but the ocean crust did not move. So remember, right, that basically means that the continental crust is plowing through the ocean crust and just kind of leaving this trail of destruction behind it. Now, geophysicists definitely disagreed with this statement. They thought that the ocean floor didn't have enough strength to hold the continents in place, right? So that way, basically they thought that the continental crust could pretty much wander wherever they wanted, that they wouldn't be able to stand still at all. Now, what was really interesting is, like I said, Wagner's ideas were definitely pushed aside, right, after he came up with them. However, in the 1950s and 60s, we started studying the Earth's magnetic field. And we started to figure out that the Earth's magnetic field varied through time. And this is what's really going to be part of the key that helps us understand that Wagner was actually right. Wagner wasn't actually crazy, that the continents are in motion. So let's again revisit Earth's magnetic field. So what produces the magnetic field is we have a liquid outer core that's rotating on top of the inner core, right? So here's our inner core, and here's our outer core as far as the Earth goes. So both of the outer and inner core, remember, are made up of metals. So I've got a liquid metal, right, that's rotating, right, on the outside of a solid metal. Well, that's going to create basically a charge, right? So that charge is the electric field, the magnetic field itself. So this charge makes the Earth act basically like a giant magnet, as the charges flow, right, from negative to positive. Now again, what's important to notice is that the geographic pole is not the same spot as the magnetic pole. You can see there's actually an 11.5 degree difference between those two. So the Earth doesn't rotate straight up and down, it's tilted a little bit. So because the geographic and magnetic pole is not parallel, this is what allows us to come up with the idea of declination. And you've heard of these things before. Maybe you haven't heard of the word declination, but you've heard of latitude and longitude. So I want to talk to you just for a few minutes briefly about where we get those numbers. So when you look at a compass points to magnetic north, not geographic north. So if we look at this compass here, right, this compass is pointing towards actual north, right, so magnetic north, not the geographic north. So the difference between them, right, this angle here, is what we call declination. So the declination obviously completely depends on the location of geographic north and magnetic north. This is where we get longitude from, right? So longitude is basically coming from the degree of these angles, right? As you move, right, throughout the continents and throughout the planet, right, those angles are going to vary, and that's where we get the longitude from. Now, if we look very specifically at these lines of force, I want you to notice, and let's trace out one of these lines of force here again. So the line of force, right, as you can see, comes out of the Earth and then goes back in. So if you were standing right here, excuse me, please read there, if you were standing right here, right, that line of force would be perpendicular. However, if you were standing right here, notice that line is parallel. Okay. So that arc shape, right, that it creates, right, makes perpendicular and parallel lines. Okay. These angles, right, between the lines is what we call magnetic inclination. This is what gives us latitude. So that's pretty important. It also gives us something else here that's pretty important. Let me clear this stuff. So I want you to notice on this picture here we have a compass needle, and that compass needle, okay, you can see it's kind of set right on this pin here. So the compass itself, right, can move, right? Right, it can point to north and south and west and east, right? It can move this way. But what you may not realize is that compass can also move up and down. So it can kind of, it can look like that, or it can look like that, right, as you see in these pictures. What it's doing, right, obviously as it points to north and south, that should tell you what it's doing, right? It's lining up with magnetic north and south. However, when it starts to tilt like this, up and down, or maybe it sits parallel, is it's lining itself up with this line of force. So again, like I said, if you were standing here, that line is just about perpendicular to you. Well, notice that compass is also sitting perpendicular. If you were here, that line of force is parallel. Again, notice, right, my compass is parallel. So this is a neat trick, right? Let's say you were dropped off on some continent and you have no idea where you are, if you're close to the pole or if it's close to the equator. Well, you can actually look at the tilt of the compass itself, right? Look at the tilt of the needle. And that would tell you whether you are close to the pole or close to the equator.